Passive dynamic walkers, as the name suggests, ideally do not need any external actuation to continue their walk indefinitely, but in reality, they show steady state variability, which adds stochasticity to their dynamics. So this paper that we're discussing today addresses on how we can measure this in terms of mean first passage time for the system to reach various states within state space. So the actual topic of our paper is predicting the mean first passage time to reach any state for a passive dynamic walker with steady state variability. Starting for the basics, what is a passive dynamic walker? A passive dynamic walker is a simple form of legged locomotion which can move down a slope without actuation. Its only source of energy is gravity. So how these work are, the energy lost in friction in collisions are balanced, and friction are balanced by the conversion of potential energy to kinetic energy as the walker moves down a slope. However, in reality, variability and imperfections in the walker and the environment results in steady state variability, even in seemingly ideal walkers on seemingly even slopes. Researchers have been commonly using a simple passive dynamic walker called the rimless wheel to understand the coupled dynamics of the walker and the ground. So in this paper also, we use the same extensively. The variability in real-life passive dynamic walkers' limit cycles make them behave as metastable systems. So by definition, a metastable system is a dynamic system with long life cycles and yet guaranteed to fail as time tends to infinity. So the diagram on the right is often used to describe metastable systems. So the red ball in position 1 is said to be metastable, where a small perturbation will effectively result in conversion back to state 1, while a larger push that pushes the system to beyond state 2, when that happens, it will escape the metastable attraction field and end up in state 3. So using this analogy for a rimless wheel, small slips and bumps in motion would be corrected automatically back into steady state walking, while larger variations would force the system into failing, or in other words, stopping its motion. Okay. So in the topic of improving stability of a passive dynamic walker, there are two main paths one might take. One is in the design phase, when the design parameters are optimized by evaluating the stability of the system for bounded inputs, and the other is by using real-time adaptive control. Designs of actuation-based controllers for otherwise passive walkers usually have two main objectives. The main one is to increase the lifespan of the system, obviously, and also we would also want to achieve maximum energy efficiency, because the idea behind a passive walker is not to use energy. So applying an external force to actuate an otherwise passive dynamic motion is a complicated task, because an incorrectly applied actuation could easily drive the system into failure. Therefore, it's important to select an actuation form, level, and timing correctly. A popular metric used to measure and optimize on a walker's performance is the expected time to failure. Methods that take a Markov chain approach using an eigenmode analysis on the state transition property matrix are limited to providing a global value for reaching the absorbing state or the failure state. A global mean first passage time prediction is a valuable tool in optimizing stability through system parameters. But in contrast, if a method is available which is able to predict time of arrival at any state, including a failure state, is a better candidate for a feedback signal for a closed-loop controller of a passive dynamic robotic walker in order to make behavioral corrections only when needed. So in other words, if we can develop a method to calculate the mean first passage time to reach any predefined target state, which is the time taken for the state vector to first reach a target T starting from any given source point S, that would be more useful as a feedback signal. So with that background, moving on to the contributions of this paper, we firstly develop a model to predict the mean first passage time for a passive dynamic walker to reach an arbitrary state. For this, we use we developed an extension of a powerful method presented in the Nature Journal. And then we model the system state of a passive walker on the return map space of its angular velocity at collision. To describe this, we use the dynamics of a rimless wheel, and we show that the state transitions for the walker can be modeled as anisotropic random walks in the state space. After that, we compare the predictions of experimental data of the rimless wheel with Markov chain-based methods and show that we can get a 10% higher prediction accuracy with the proposed methods. And finally, we'll present a minimal intervention controller for a rimless wheel. The mean first passage time prediction to reach identified states are used in this controller as feedback signals, so that external torque can be applied only when necessary to economically postpone failure. And finally, we compare the controller's performance with that of a PID-based controller. The simple passive dynamic walker that we use in this paper to discuss and develop models is the rimless wheel, as I mentioned earlier. So the idealized rimless wheel has several assumptions, including point mass at hip, no slip, impulse collisions which are inelastic, and an instantaneous transfer of support between legs at collision. When the system state is expressed in terms of the angular velocity just before collision, or omega, the steady state remains unchanged for a fixed ramp slope, irrespective of the starting states. The state transitions of omega on its return map space behave like random walks initially biased towards a tractor at the steady state. So we will use the experimental and simulated data of a rimless wheel to discuss this further in the next slide. So the left, this video captures the motion of the experiment, one run of the experiment of which the data that we used. And the right-hand side is the same experiment data on a MATLAB simulation. On top, while the same motion is mapped into the return map space of angular velocity at collision. So the y-axis here is the angular velocity at step n, and the x-axis is the angular velocity at step n plus 1. So as you can see, when we look at the ensemble of all trials, it looks as a random walk that is biased towards the steady state attractor somewhere around this point. So I'll just fast forward. So this shows all the trials together. Okay. So here is a plot of angular velocity for a part of one experimental trial. So the sharp drop of angular velocity during each collision has a lot of variability, as you can see from the difference in the drops. And the figure on the right shows the probability density distribution of the return maps at each collision number for all trials. So the wider the distribution, the more variability. And as you can see, once the walker converges into this metastable motion, while lower, there still exists considerable variability. In addition to this experimental data, the rimless wheel motion was simulated also to get a larger data set. So the first three set of figures shows the various forces acting on the rimless wheel in 3 positions. The first is just before collision, and second one is just after collision, and the third one is with the colliding leg vertical, which is a state in a cycle with the lowest angular velocity. And the figure on the right shows the variability in state transitions for the simulated data as well. So there's variability still here. And all the steps and data sets for these simulations are included in the paper. It's supplementary information and references. Going on to the next one. Now that we have the data sets for the motion of the rimless wheel modeled as biased random walks, we can move on to the mean first passage time calculation methods. So general methods for mean first passage time estimation for random walks have advanced to finding really efficient methods for specialized networks, such as scale invariant media, those on fractals, anomalous diffusion, scale-free networks, networks with bounded domains, Levy flights, and Brownian motion. However, when the random walks are results of state transitions for real-world dynamic systems, such ideal conditions are rarely met. These walks are anisotropic and commonly biased towards the attractors formed by nonlinear interaction dynamics between the system and the environment. As we saw in the rimless wheel motion data as well. So generally, random walks are described in terms of 2 characteristic dimensions. The first is the fractal dimension, or DF, as we call it here, which characterizes the density of the nodes in the network. It's usually calculated using this equation, where NR is the number of nodes within a sphere of radius R. And then the other one is the walk dimension, which characterizes the ease with which the walker can move through the network. And it's calculated using the exit time for the walker of a sphere of R radius. The relative magnitudes of these dimensions show different walking features. So when the dW is less than dF, we can see non-compact exploration. That is, the walker moves further away from the source with time. The dependence of source location is lost soon when the distance to the target is higher. And the other part of it is compact exploration. As the name suggests, each node is eventually visited as obstacles make it harder and slower for the walker to move away from the source. Okay. A very versatile method of calculating the mean first passage time in complex scale invariant media was proposed in a popular article published by Nature. So let's start from the given equation for the propagator. The W is the probability density distribution of being at target point T at a time simple t, starting from source point S. This is obtained by integrating for time t the product of the probability density that the first passage time to reach target t starting from S is t bar, and multiplying that by the probability density of returning to target t starting from the same state t in a time t minus t bar over t bar. So using this equation, they introduce a function h, which is the integral as time tends to infinity, the propagator's probability distribution minus the stationary probability distribution of that network. They have shown that h can be approximated by the infinite Green's function, which helps to solve this equation. And using that, they derive a precise equation to calculate the mean first passage time. The detailed steps of these derivations can be found in the cited article here. For this paper, we are only interested in the final result, which is in this pink box. Basically, they provide with a straightforward equation to calculate mean first passage time, given the transport dimensions df and dw. And here, n is the number of nodes in the network, R is the distance between the source and the target, and A and B are constants for a given system. Okay. When adopting this method to predicting the motion of a passive dynamic walker, as well as many other real-world situations, one important difference needs to be addressed. That is to account for the bias in the state space imposed by metastable motion and absorbing states. To do this, we looked into how we can bias modify the transport variables df and dw. So in the existence of network bias, the calculation of df remains unchanged because this is the density of nodes in the network, and it's solely a property of the network and not the walker. So we can use df as it is. However, dw or the walk dimensions should account for any obstacles or potential fields shaping the walk. Here the top chart shows how the dw changes with the relative angle of the line joining source to target to that of the direction of the bias. On the other hand, the probability of reaching a target is the highest in the direction of the bias. So what we wanted here was to get a generic bias modified walk dimension, or DWB as we call it here, to be used in the mean first passage time predictions. To get something of that sort, we used a collection of simulated networks with different noise levels. So as you can see, these are three example networks that we use. The first one is without any noise, and we keep on adding noise to this. To create a biased random walk, we've used an elliptical probability density distribution at each step to select the next step. I think this would be more clear looking at the video here. So at each step, we used a probability density distribution to select the next step. And because of the bias, this is elliptical in shape. We have a few examples here, but I think that should be enough. With several hundreds of scenarios tested on different networks, source, target, and bias combinations, we got a generic equation to calculate DWB as given in this pink box, which I would say is the main contribution of this paper. Again, more details of these calculations and results are included in the paper itself. So we use the newly derived DWB in the mean first passage time prediction equation from nature to calculate the mean first passage time in biased networks. So this slide shows comparisons of mean first passage time predictions for several source, target, and network combinations. So here the x-axis is the distance between the source and the target, and the y-axis is mean first passage time. The black dots are the actual first passage times marked there. The blue lines are the predictions using the proposed methods, and the green line are the predictions using the conventional walk dimensions. So as you can see, for all these scenarios, the blue lines give a better prediction. Okay. Next we apply the proposed mean first passage time prediction method for rimless wheel data. The first chart compares the actual first passage time to that of the predictions, similar to the charts shown earlier. On the right-hand side, it shows a comparison of the mean first passage time to fail using the proposed method and that predicted using the eigenmode analysis of transition probability matrix. The details of this method is also included in the supplementary information with the paper. And we were able to see that there was a 10% increase of accuracy in the experimental data set. However, the more important part here is that the proposed method was capable of predicting mean time to reach other states before reaching the failure state, which is important in terms of controlling the motion. So we use this mean first passage time prediction here in a minimal intervention control, as we call it. So what we do is initiate motion and wait for the system to reach steady state. And we keep measuring omega at each collision. And then with that omega, we calculate the mean first passage time to reach our defined target. And if that is lower than the threshold, only we apply an external torque. Otherwise, we just keep on monitoring, letting the walker continue its passive motion. Okay, finally, this is a comparison of the controller to a scenario using a PID controller. So the PID controller, what it does is it also monitors the angular velocity at collision, and it uses a threshold angular velocity instead of mean first passage time. So when the velocity drops below that threshold, it applies a torque. So these are two different scenarios that we tested against. So the green lines are the mean first passage time obtained with the PID controller, and the blue lines are with the proposed controller, with different thresholds that we tested against. So the R-square value of 0.96 was possible with the use of the bias modified transport variables, and around a 40% longer lifespan was obtained using this controller with respect to the PID-based controller. In addition to that, the PID-based controllers required about 25% more applications of external torque. Finally, there's a few points that I'd like to mention before finishing this presentation. So firstly, the proposed method can be used to evaluate alternative control policies or parameter changes of a given control policy by testing whether the new solution improves the mean first passage time or not. The proposed method is able to predict accurately even when the state transitions show anisotropic probability density distributions. And finally, in contrast to reward-based policies, the proposed method uses the feedback signal of the state transitions for the system, and the control policy does not require the system to learn a value function. So with that, I will end my presentation, and thank you all for staying online. If there's any questions or other points you'd like to bring forward, that would be awesome. So
thanks, Isri. It was really nice. Yeah, I have a few questions. Can you go back to your bias modified? No, let's go back to the walk dimensions and the fractal dimension.
yes, this one.
Yeah. So the DF. Now the fractal dimension is a number of nodes visited when it passes a sphere of a ball of radius r, right?
Actually, it's a number of nodes
visited, yeah, or number of nodes inside
the sphere of R. Yeah, that's right.
Yeah, it is not really the visited number, right?
No,
it is right. So it is the number of nodes. So that says something about the density of nodes. Right?
Density of nodes. That's exactly what it is.
Yes. Right. So the fractal dimension.
Yes.
And then the walk dimension is how they are connected, basically. Probability of transition from one to another. So if the walker is stuck in that sphere, it's very difficult to escape, right?
Yes.
So if dw is high.
Yes.
Yeah. Okay.
That's right.
So those are the two things. Okay. So now, when you go to the biased modification dwb. Okay, let's go back to that equation, Green's function.
This one.
Yeah. So what is W here?
So yeah, W here is the probability density of being at target point T, starting from source point S in a time simple T. And yeah, it's obtained by integrating for time t the product of the probability density that the first passage time being t bar for the walker to start from source S to reach target t, and multiplying that by the probability density of returning to target t starting from the same point t in a time t minus t bar overall t bar.
Yeah, okay, so that is in this paper, right, in the bottom.
Yes, yes, they have a very detailed derivation of this.
Okay, yeah, I think it is good to have that. Okay, so and then can you go to the biased modification?
This one, or
And yes, no, that equation, pi by 2.
sure, this one, yes.
Yeah, so then here, like to do the DWB, you have to know DW, right? So
Yes,
how do you know the DW in a bias kind of?
yeah, that's a good question. So DW we got straight from this equation itself. I should have mentioned that before. So using the simulated data, we can get the DW from this equation, and if we can get that, so what we did was we got this, and then we got the actual mean first passage times from this, like something similar to this, and then we assumed the DWB was the optimal one, and then try to plot that into this equation. So instead of DW here, we use DW. This is what
the
we
thing
try
is,
to.
like, again, if you explain how now DW is taken from simulations, you said, right?
So yeah, DW we got from simulations, but we kept it aside. We didn't use it up to this point. So DW was there, and then we used this equation.
But how, when you do simulations, if real DW is DWB, how is it different? Like, how can you have two DWB? Is that right? Oh, no. So okay, so you let the walker go in the state space, and then you use the previous equation to get the DW, right?
Yes.
You basically calculate the T exit.
Yes.
Yeah,
So
T exit for what?
So
For
we
different radii.
for different source target combinations and different bias and network combinations.
Right. How many combinations?
We used around, I think, 200 or something around that number.
200.
Yes.
Okay. So you get different. So you keep the bias probability distribution the same, right?
Yes, that's right.
When you calculate the DW.
Yes.
So you get a walker, and then you set a probability distribution, and then you get your DW, right?
Yes.
And then you put it here, and then this DWB bias modified one is used in the MFPT prediction. Okay.
Yes. So actually,
I see.
in,
So
in
that
these
means, like, so you
equations,
need a history, right? You need the walker to have a history to know DW.
yes, exactly. So in this equation, we knew mean first passage time, we knew N, we knew R, we knew F. So DW was the DW, and the two constants were the only things that we didn't know. So what we did was we did a curve fitting with this equation to find DW, and then we plotted this DW with the DW we got from like the conventional DW. And then try to find a sort of relationship between the ideal DW and the DW we got there.
So in that case, how do we use it in a real-time situation?
So in a real-time situation, because all of these finally converge into this equation, instead of using the DWB as the conventional equation, we use this one in this space. So in a prediction, what we don't know is the mean first passage time, but we know N, R, DW, and DF.
Okay. Right. Okay. So that means, let's say if it is real time, right? So that means like there's no history, and then I'm just going to a new situation. I have to make a rough estimate of MFPT based on the little history I know, right? Is that right?
Yes, that's true. Yes.
Yeah. Okay. The more I know, the better, right, about
Yeah.
that situation. Okay.
Yes.
So
Yes.
that means like, so we can have basically memories of DW for different situations, and we can expect to use them in our estimations, right?
Yeah. Yes.
Okay, something like that. Okay, that's I'm just thinking of extending.
So,
Right.
one of the drawbacks in this method that we have mentioned in the paper as well is the accuracy of the prediction is dependent on the accuracy of the data we use to get these transport variables.
Yeah. The accuracy of the data. It's like, it totally depends on the history, the knowledge of the history, right?
Yes. Yes, that's right.
Yeah. Okay. So, Liang and Ali, do you have any questions? Maybe you have to unmute.
Thank you very much for your presentation. No, I don't have any questions. Thank you.
Thanks, Ali.
Yes, this is really good. The only question I have is, do you know if such method can go beyond the passive dynamic Walker cases for a higher dimensional system or most states involved?
That's an excellent question, Liang. So as long as we can map the dynamics of a system to a random walk or a biased random walk on a state space, we can apply this method. So as a matter of fact, we have used this same method on a completely different scenario of predicting cyclone, the paths a cyclone would take. So your question, to answer your question, yes, we can do it as long as we can map the state transitions as a random walk on any given state space.
Great, thank you very much.
Great, thanks, Isri.